Okay, these are the pre-calc notes for section 5.1, the second day. And I've just put a copy of the Pythagorean identities above example 5 so that we could refer back to them. They should be in your notes packet a couple pages prior to this. If you look at the examples in number 5 here, it says they want us to simplify the trig expressions so that they are a power of a single trig function. If you notice, there's several different trig functions in each one of these examples, and they want us to convert it so we're down to a single trig function. All right, so for the first one, notice that there's some squares involved and some ones, which should jog your memory and say, that looks something like a Pythagorean identity. We can take any of these and we can rearrange them. All right, we can solve for, say, the cosine squared in this first one, or we can solve for sine squared. So if we rearrange this top Pythagorean identity, if I subtract sine squared to the other side, it now looks like this. Cosine squared theta equals 1 minus sine squared theta. Okay? Well, that's what we have as our numerator, 1 minus sine squared theta, or 1 minus sine squared x. So we can convert this and say 1 minus sine squared x is the same as cosine squared x. All right, looking at the denominator involves a cosecant squared. So looking at our Pythagorean identity on the bottom there that has the cosecant in it, I'm looking for cosecant squared minus 1. So if I subtract the 1 over here, I have cotangent squared theta equals cosecant squared theta minus 1. And that's what I have as my denominator. So I'm going to replace my denominator with cotangent squared of x. Okay? And now I'm going to rewrite cotangent and think of it in terms of sines and cosines. All right, so we've got cosine squared x as our numerator, and I'm going to rewrite this cotangent squared would just be cosine squared over sine squared. Okay, and dividing by a fraction is the same as multiplying by the reciprocal. So we have cosine squared x times the reciprocal of this red part. So I'm going to get sine squared x divided by cosine squared x. And then our cosine squareds are going to cancel each other out. So we end up with this equaling just sine squared x. And we've done what they asked us to do. We converted it into a single trig expression. All right, let's look at our second one here. We've got cosines, we've got sines, we've got 1 minus sines. It's asking us to subtract these two fractions, and in order to add or subtract fractions, we do need a common denominator. So let's multiply both sides by the opposite denominator so that we can get this to match. So I'm going to take cosine of x over 1 minus sine of x, and I'm going to multiply top and bottom by a cosine of x. Okay. Then it says we are subtracting. On the other side, we have sine x over cosine x. And to get these denominators to match, this one needs to be multiplied by 1 minus sine x. Okay. And now if you look at your two denominators, they both have a cosine x and a 1 minus sine x. All right, so let's combine our numerators. Cosine x times cosine x would be cosine squared x. On the other piece of our fraction here, we've got sine x times 1 minus sine x. If we distribute, we have minus 1 sine x, and a negative times a negative becomes a positive sine squared x. On the bottom, we have a cosine x and we have a 1 minus sine x quantity. All right. Looking at the numerator, notice that there is a cosine squared and a sine squared that are being added together. These two pieces just add up to 1. Remember our Pythagorean identity, sine squared plus cosine squared is 1. So this becomes 1 minus our plain sine x over our denominator. And then you'll notice that we have a common factor. We have a 1 minus sine x on top. We have a 1 minus sine x on the bottom. Those are going to cancel out. This becomes 1 over the cosine of x. But 1 divided by the cosine of x, or the reciprocal of cosine of x, is secant of x. So this would be simplifying it down to just a single trig function. All right, our third example is going to require that you go back and look at a few of our identities dealing with cofunctions, all right, complementary angles here, and dealing with opposite angles. All right, so pause the video. I want you to go back and find out what is the tangent of pi over 2 minus b, minus beta, and what is the cosecant of the opposite of beta. You should have those on the previous page in one of your identities. Okay, so tangent of pi over 2 minus beta is equivalent to cotangent of beta. So we have a negative in front of it. We're going to have to keep that negative. All right, so we're going to have negative cotangent of beta. And then the cosecant of the opposite of beta is the same as negative cosecant of beta. Okay. Now, the reason we converted those is we want everything in terms of beta. We don't want things like complements of beta, opposite of beta. We need them all to match so that we can cancel common things. All right. Looking at the denominator now, cotangent squared beta plus 1. If we go back up here, cotangent squared plus 1 is equivalent to cosecant squared. So I'm going to convert my denominator into cosecant squared. Okay, and notice in the numerator we have two different negatives being multiplied together. Those are going to cancel each other out. We end up with cotangent beta times cosecant beta over cosecant squared of beta. And we can reduce one of those cosecants out of both. So we can take one off of here and one off of here. So we just have one left. So now we have cotangent beta divided by cosecant beta. All right, let's convert everything into sines and cosines so that we can get these to be in similar trig functions. We can look at what we can reduce. Cotangent is defined to be cosine over sine. And then 1 over cosecant, or the reciprocal of cosecant, would be sine. Okay, so cosecant, because it's on the bottom, when we flip it up, it becomes the sine of beta. And now we can reduce this common factor. And so our final answer is just cosine beta. Okay, our second example for today deals with solving trig equations. It says to simplify the expression and or rewriting them in a more useful equivalent expressions is very helpful when trying to solve trig equations algebraically. So the first example here says find all values of x in the interval from 0 to 2 pi, so within one rotation around our unit circle, that solve the equation cosine cubed of x divided by sine of x equals cotangent of x. So again, one trick is to convert things into sines and cosines, because all of our other trig terms can be defined in terms of sines and cosines. So I'm going to start out changing cotangent into cosine over sine. Okay. And if I multiply both sides by sine x, it's going to cancel on the bottom, which basically means that my numerators, cosine cubed x, has to equal cosine of x. All right. What we need to do now is get everything to one side so we can try to factor that expression. So I'm going to subtract a cosine of x over to the left side, and now I have it equal to 0. And I can factor out a cosine from both of those. Okay, so I have cosine of x times cosine squared of x minus 1 equaling 0. But cosine of squared x minus 1, that should look like one of our Pythagorean identities. So let's go back and look at what we have. We have the identity that sine squared x plus cosine squared x has to equal a 1. So if I want cosine squared minus 1, I have to bring the 1 to the left side, and that means the sine squared is going to have to go to the other side. So I end up with cosine squared x minus 1 is equivalent to negative sine squared x. So I can do a replacement and write this as negative sine squared x. Okay. Get that out of our way here. All right, so we've got it in factored form. We have it equal to a 0, which means each of those factors could be a 0. So I need to find where is the cosine of x equal to 0, and where is negative sine squared of x equal to 0. All right, let's start with cosine. Think about going around your unit circle. Where on the unit circle do you have a cosine of 0? That means we need an x coordinate of 0. And that happens for x values at pi over 2 and also at 3 pi over 2. Okay? We've got negative sine squared of x equaling 0, which means sine squared of x would have to be 0, which means if we square root both sides, the sine of x has to be 0. Okay? So where on our unit circle is sine of x equal to 0? That happens at 0 and at pi. However, if you look back at our original statement, we had a sine of x in the denominator, which means we can't have sine of x being 0. So we're going to actually have to ignore those two possible solutions since it makes our original expression undefined. Okay? All right, looking at our second example here on this page, example 7, it says to solve the trig equation by factoring, find all values of x in the interval from 0 to 2 pi where 2 sine squared of x plus sine of x equals 1. So let's get everything to one side again since we're going to be trying to factor. We've got 2 sine squared x plus sine of x minus a 1 equals 0. And then let's go ahead and factor that. It's kind of like just saying 2x squared plus an x minus 1. It's just that instead of x's, we have sine of x's. All right, we're still trying to factor it. So this would factor into 2 sine of x and sine of x. To get a negative 1, we need a 1 and a negative 1. And we just have to decide where our negative needs to be so that we end up with 1 sine x in the middle. So if we make this outer piece positive 2 sine x and our inner piece negative 1 sine of x, that would add up to a 1 sine of x. All right, so let's look at each factor here. So we need to take 2 sine of x minus 1 and say when does it equal 0? And we need to take the sine of x plus 1 and say where does it equal 0? If we solve, we'll start with the one on the right here. That is saying that the sine of x would have to be -1. So where on my unit circle do I have a y-coordinate of -1? That would be right here at 3 pi over 2. So my solution to this second one is x could be 3 pi over 2. All right, looking at the left side one, we have 2 sine squared minus 1, 2 sine of x minus 1 equals 0. So 2 sine of x would have to equal 1, or the sine of x would have to be 1/2. So where on my unit circle is the sine equal to 1/2? We have a point here, and we have a point here. Both of them have a reference angle of pi over 6. So for my answers here, let's move this out of the way. We have x could be pi over 6, or in quadrant 2, we would be at 5 pi over 6. All right, so we have 3 solutions. X can be pi over 6, 5 pi over 6, or 3 pi over 2. All right. Part B, it says find all solutions to the trigonometric equation 2 sine squared of x plus sine of x equals 1. That's the same exact equation that we just solved. However, notice that in the part A, it said we needed all the values of x in the interval from 0 to 2 pi, meaning if we just go once around the unit circle. But in part B, it says we can list every single solution. Well, we can't list all of them individually, since we can't go around the circle an infinite number of times. We'd be here forever. So what we're really looking at is take all of the angles that we found. We found one to be pi over 6, we found one to be 5 pi over 6, and we found one to be 3 pi over 2. And what we're going to do is we're going to just say, well, we could just keep going around the circle. If we keep adding 2 pi to that, we are going to land in the same spot. So for example, here I went up pi over 6. Well, if I went around a second time and landed there, I've just added 2 pi to my angle. So we are going to add 2 pi to both of these, or to all 3 of these. But we could add 2 pi, we could add 4 pi, we could add 6 pi, we could add -2 pi. We can really go around the circle in either direction an infinite number of times. So the way we represent that is we just put an n in there, just to say that n is an integer, and that means we can go around an infinite number of circles. So we've got our solutions being x equals pi over 6 plus 2n pi. We have 5 pi over 6 plus 2n pi. And we have 3 pi over 2 plus 2n pi. All right, the next set is kind of a mixture of things. It says solve each of the following such that our angle is between 0 and 2 pi. Do this without a calculator, but you will be referencing your unit circle. All right, so the first one says 2 sine x plus √3 equals 0. If we solve for the sine of x and get that by itself, we would have 2 sine of x having to equal -√3. Dividing our 2 over, we are saying where is the sine of x equal to -√3 over 2. All right, so if you reference your unit circle, having a sine of √3 over 2 means a reference angle of pi over 3. Okay, sine is going to be negative in quadrants 3 and 4. So picture being in quadrant 3 or 4 with a pi over 3 reference angle. We could be here or we could be here, with this being pi over 3. Okay, so starting from 0 to go to here, we would get 4 pi over 3. And going all the way around to this one gets me 5 pi over 3. Okay, again, you could find those right off of your unit circle. All right, our second one says 4 secant squared of x equaling 8. If we divide out the 4, we're saying the secant squared of x equals 2. We can square root both sides. So secant of x equals positive or negative root 2. And then let's think in terms of cosine, since we have cosines and sines on our unit circle. That would mean the cosine of x would equal the reciprocal of that, 1 over root 2, or if you rationalized it, root 2 over 2. So where on the unit circle do we have cosines of root 2 over 2 or negative root 2 over 2? And that is all of our pi over 4s, or our 45-degree angle ones. So our x could be pi over 4. We could be in quadrant 2, where we have 3 pi over 4. We could be in quadrant 3, where we have 5 pi over 4. Or we could be in quadrant 4, where we have 7 pi over 4. All of those would be solutions to that equation. All right, example C. Solving and trying to get that cosine of x by itself. We would have to add a 3 and divide a 4 over. So we've got the cosine squared of x equaling 3/4. Square rooting, we would have the cosine of x equals plus or minus the square root of 3 over 2. We're just square rooting both the 3 and the 4. So cosine of x is positive or negative square root of 3 over 2, which is all of our 30-degree or pi over 6 angles. So in quadrant 1, we would be at pi over 6. In quadrant 2, we are at 5 pi over 6. In quadrant 3, 7 pi over 6. And in quadrant 4, 11 pi over 6. Those all have reference angles of pi over 6. All right, question D. It says the sine of x has to equal the cosine of x. So if you think about your unit circle, we're basically saying in our coordinates, where is our xy pair matching? In other words, our x has to be the same as our y, so that our cosine and our sine are identical. And that happens with our ordered pairs where we have the root 2 over 2's. So we could be at a root 2 over 2 where they're both positive, which means that we have an angle of pi over 4. Or we could be at negative root 2 over 2, negative root 2 over 2 in quadrant 3, where we would be at 5 pi over 4. So both of those angles would have sine values that equaled their cosine values. Okay, example E. Notice that we have cosines on both sides. Let's get everything to one side and we can try to factor it. So 2 cosine squared x minus cosine of x equals 0. We can factor a cosine out. That leaves us with 2 cosine of x minus 1. And then let's set each of those equal to 0. So cosine of x could be 0, or 2 cosine x minus 1 could be 0. All right, so looking at our unit circle, where is the cosine of x equal to 0? That happens at 90 degrees, or pi over 2, and at 270, or 3 pi over 2. Okay, for the second part, we would have to solve for cosine of x. Add a 1 over, divide a 2 over. So we're saying the cosine of x has to be a 1/2, and that happens with our pi over 3 angles. So pi over 3 in quadrant 1, and then we also have a positive cosine in quadrant 4, which would be at 5 pi over 3. All right, and the last one for today. We have 2 plus 2 cosine of x equaling sine squared of x. Now notice in this one, we have two different types of trig functions. And if we were going to try to factor this, we would want everything to be in terms of the same trig function. So I'm just going to move a few things out of the way here so we have a little room. All right, so let's change this sine squared using one of our Pythagorean identities. And we said that sine squared plus cosine squared is 1. So we can rewrite this sine squared as 1 minus cosine squared. Okay, by subtracting our cosine squared over. So I'm going to rewrite this. We're going to say this, our equation is 2 plus 2 cosine of x equals 1 minus cosine squared of x. And now everything is in terms of cosines. It's going to make it a lot easier to solve. So let's bring everything to one side. I'm going to subtract a 1 over, and I'm going to add a cosine squared x over here. All right, and let's put things in order here. So we have cosine squared of x plus 2 cosine of x plus 1, if we take 2 minus 1, gives us a 0. Okay, and if we factor that, that factors into cosine and cosine. To get a positive 1 and a positive 2 in the middle, we need both positive 1s. So we're going to get two identical factors. So we're really just saying, where is the cosine of x plus 1 equal to 0? Come on. All right. So finishing up, that means cosine of x would have to be negative 1, which happens at our angle of pi. All right, so we're going to stop there for today. Our second day's assignment is here. We're working on page 410, and we have a list of questions here for you to try.